The other significant detail that I wanted to be sure to cover is the connection between the units on K and the overall order of the rate law. If I were to take this rate law, rate equals K times a to the m, and rearrange this equation to solve for K, I would divide both sides of the equation by a raised to the mth power. And thanks to my 8th grade math teacher, when I write something like this and clean it up, I have to flip it around so the thing we solved for is on the left. And so we get that K is equal to the rate divided by the concentration of our reactant raised to the order of the reaction. So I want to just focus on the units. What units are going to fall out of this for various orders of the reaction? Remember, order means that exponent, m. So as m takes different values, how does that impact the units for K? And so what I'm going to do over here is just set up a table. We're going to look at the units of K versus the order. Okay, let's say that this is a 0 order reaction. Okay, if this is a 0 order reaction, down there in the denominator, a to the 0 is 1. And so K is equal to the rate, and rate has units of molarity per second. I'm going to write the per second as seconds to the minus 1. Okay. Let's say that m is equal to 1. Okay, when the order is 1, then rate has units of molarity per second. Okay, so let's see, maybe I can write this out over here on the same line. The rate has units of molarity per second. That's what's in the numerator. And down in the denominator, we're going to have molarity raised to the first power. So molarity just cancels out. And the only units that are left are seconds to the minus 1. I guess I should put over here work. Go ahead and make this a 3-column table. Back up there when the order was 0, we had units of molarity per second for the rate divided by 1 in the denominator, so we end up with molarity per second. Well, let's take a look at this for a second order reaction. For a second order reaction, up in the numerator, we have molarity per second, and in the denominator, if m is 2, we have the concentration squared, so that'll be units of molarity squared. Because remember, when we do something like squaring, we have to do it not just to the number, but also to the unit, so the molarity gets squared. Well, there's 1 molarity in the top and 2 in the bottom, so one of those will cancel out. And if I have molarity in the bottom, that's the same thing as writing molarity to the minus 1, and then I still have the seconds to the minus 1. Okay, let's do one more of these. Let's do a third order reaction. Up in the top for the rate, I'm going to have molarity per second, and down in the denominator, if it's third order, we're going to have molarity cubed. And again, I'm not looking at the numbers here, I'm looking just at the units part. So if m is 3, down in the denominator, we're going to have the concentration cubed, and so we also have to cube the unit of molarity. Well, I've got 1 molarity in the top and 3 in the bottom. So that 1 molarity in the top will cancel out with the bottom, leaving us 2 in the bottom. And so that becomes molarity to the minus 2 seconds to the minus 1. So let's take a look at this. For a third order reaction, the number in the power on the molarity is 1 less than the order. And ditto over here for a second order reaction, that 2 becomes a 1. Now there's that negative sign, don't forget about that, but just in terms of the size of the number. When it's third order, that number becomes a 2. When it's second order, that number becomes a minus 1. When it's first order, we get molarity to the 0, right? Because 1 less than 1 is 0, molarity to the 0 is 1. And then in the case where it's 0 order, if we take 1 less than that, we get a minus 1, but a minus 1 raised a minus 1 times a negative gives us a positive 1. So anyway, I'm going to summarize this on the next page. Okay, so to try to summarize the pattern from the previous slide and to generalize it just a little bit, let's say that our rate law is the rate is equal to k times a to the m times b to the n. The important thing to focus on is the overall order. So if you have more than one reactant there in your rate law, you just want to add the exponents to get that overall order. K has to have units that will combine with what we get from A and B to give us molarity per second. And so the shortcut is, if you know the overall order of your reaction, you subtract 1 from it, and then you turn it into a negative number. And so the units will be molarity to the minus 1 less than the overall order, and then your time to the minus 1. Most of the time in these reactions that we're looking at, the time is seconds, but it could also be minutes, hours. It just needs to be some sort of time unit. Okay? And so here's why this is so important. It's a fairly common device on a test to see if you really get the units. To give you the rate constant with units for a reaction and then expect you to figure out what the order of the reaction is from that statement, right? So they expect you to use the units of the rate constant to figure out what the order is. So that it might be an integrated rate law type problem where they're expecting you to do something with the 0, first, or second order integrated rate law, but they won't tell you it's a first order, but instead they'll tell you that they'll tell you that the rate constant is 0.5 per second. And from that, they expect you to be able to determine that's a first order reaction. Let's take a look at an example. Okay, here's the example. What is the order of a reaction if its rate constant is 2.4 times 10 to the minus third per molar cubed per second? Now, I've been writing all of these a little bit differently. I've been writing the units with negative exponents. So this would be 2.4 times 10 to the negative 3, and then molarity to the minus 3, and seconds to the minus 1. Okay, so here's the pattern. This number right here, 3, is 1 less than the overall order. So the overall order has to be 1 more than 3, which is 4. So this is going to be a fourth order reaction. Now, we don't have the fourth order integrated rate law as part of what we're looking at in this chapter, but we certainly can write the rate law now for this reaction. Since we know that it's fourth order, we could say that the rate is equal to K times whatever the reactant is raised to the fourth power. Now, that would not necessarily be strictly true because the rate law could depend on more than one chemical. So it might be A squared, B squared, but assuming that it is dependent just on one reactant, one chemical, the rate law would be that the rate is equal to K times A to the fourth. And so we could do all sorts of things, like since we have a numerical value for the rate constant, we could be asked to calculate the rate given a particular concentration of A, or we might be asked to find what concentration of A would give us a particular rate. So once we know that it's fourth order, we can rock and roll on those types of questions. All right, Bobcats. That wraps up this section. What we did, our two big objectives here, we used the stoichiometric coefficients to relate the overall reaction rate, the rate of disappearance of the reactants and to the rate of appearance of the products. And we also looked for the pattern in the units of the rate constant and found that the units were given by molarity, in terms of molarity to the minus overall order -1, right? So 1 less than the overall order -1, and then your time to the -1 power.